People have been talking about 3D printing and stuff like that. There is a theoretical consideration of what type of information can be missing and still be able to recover the function. And those types of theoretical questions, unless I haven't seen it in the literature, haven't really been addressed, and it could be addressed in artificial neural networks. So for example, one of the things that I keep getting hit with is, what if you have all the connectivity, but you don't have the biases of each neuron because that's at an ion channel level or something. So you could take a visual neural network and that has been trained to recognize cats and dogs or something, and say, what if I had all the weights, but if I removed all the biases? The network wouldn't work, but what machine learning techniques could be used to efficiently fill in those? How difficult of a problem would it be? Another one that comes up in whole brain emulation is, well, what if the retinas are removed, essentially, when you are trying to scan the brain? You don't have anything to ground the LGN and the visual cortex representations. So what if, same network, if you took that visual categorization network and took off, maybe it has 20 layers, but you take off only the first layer? Seems like a simple problem, but I don't think anybody has actually shown it. So this would be a research project to basically take artificial neural networks, where we really do have ground truth, and take away strategically pieces of information that really would break the network, and say, how hard is it to get that network back up and running?
Yep. So the idea would be to team up with one neuroscientist, one machine learning engineer, list the common missing information we expect to see, find the analogs in the artificial neural networks, and then just start knocking them out and experimenting and seeing how robust are we to various missing information and how can we retrieve it. So the initial money and time will be spent mostly writing the full specification for what are all the different types of missing information. And this is a 1 to 2 person just compute and spend some couple of months probably in front of a computer and knock it out. Yeah. Any questions? Yeah, we added a few more details here. Yes?
Why don't you think this is just too easy? Like, you can totally delete layers and biases with like zero effect on the network.
This is the criticism we actually get.
So is this, and what? So if you do those, if you do that, what happens?
You use like nothing. Like say, I think like the original ResNet paper, part of their argument for why it was an ensemble was that they could just delete multiple layers from throughout the network, and it made like no difference to the result. Because and that was their argument for, oh, it's an ensemble.
Biological neural networks are not residual networks.
Yeah, I know. But I'm saying why don't you think it's too easy to repair on artificial networks?
Oh, I see.
Yeah.
So I want to be, if you deleted a middle layer, okay. If you had I must be missing something, because if you have a straight layer after layer after layer, you delete one, the whole thing doesn't work.
No, the whole thing works.
The thing you're missing is that they use residual connections, so the layer is just computing an additive delta to add to a stream.
No. It didn't depend on it. I mean, obviously there are even more robust, but even just like you could just lock out entire layers and like there's no good.
Then there's no connection to the layers.
You just plug it straight into the network.
Yeah, I don't know what you mean by
that. Surgically reconnect them. Okay.
Yeah, and then if they have different dimensionality, you can put in like a little randomized step layer, and that'll work pretty well too. I mean, this is how progressive growing works. This is how net to network. This is how you go hot starting model.
And you don't do any more training afterwards? You don't do training afterwards?
You can do training, or you cannot do training. If you do training, it works even better. Then you can get even more aggressive about it.
Okay, so I can take a visual neural network and shoot it with a gun, and there's a big hole in it, and it still works?
Well, randomly losing stuff does work mostly well.
I withdraw the point.
Yeah. So there's been some research on certain types of loss, so random loss or losing particular networks, but stuff like losing 100% of the biases or a few other ones that have more biological analogs might not have been tried yet.
The thing about a residual network is this other paper showing that it's learning like an unfolding, it's learning something equivalent to the unfolding of a recurrent neural network, doing it some number of steps. So you can also take a residual network and you can share the weights over time of the unfolding stages. You get something very similar. It doesn't seem to harm the network very much. So in that sense, like removing one time step It's not gonna,
So
you're gonna
it's
get a
just like one
smooth
cycle
reduction.
in a recurrent network.
Yeah, you're just
Taking
gonna
out.
get a smooth reduction capability, not like a mass.
In a recurrent network.
Well, what about the input layer?
A residual
Remove the
network is
input layer.
equivalent to an unfolded recurrent network, unfolded over
Yeah,
several
I
steps.
know. Like
How do you input an image? I mean, if you remove the input layer of a visual network,
You just send to the next one.
and it just works without any training.
Yes, because
I want some money down.
a
on this
residual.
one,
This is
okay?
almost hold on. This is obvious for a residual network because a residual network learns the equivalent unfolding of a kernel network.
Okay.
So take an RNN and
I
just
need
skip a
to-
time step. And it's
Okay,
doing some iterative estimation thing, then it doesn't make that much of a difference. Like you get like a smooth
I was
iteration
thinking of a
loss.
convolutional.
Yeah,
network.
residual network's a special case, so I don't
Yeah, I mean, a lot of it's just that they're very linear. Like, take like style gun models. You can literally take a style gun, like trained on like cats, and a style gun trained on human, and like add them up, like sum them, just 1 + 1, parameter by parameter, to get rid of a single model, and you will get a half human, half cat output.
It's very similar actually to the
And you
way
also
that
use layer
additive tuning thing.
Anyway, that sounds fascinating.
All right, thank you guys.